Welcome to tutorial part 5. In this part of the tutorial, we're going to be creating a path for the enemy to follow. And we're doing this so that we can create more advanced tutorial AI techniques that we can sort of test against our more complex AI movement. So let's get to it. So to begin with, what we're going to do is we're going to create an empty object and we'll call this path. Then what we're going to do is create an empty on that, and I'm going to call it path node. And then we're going to add a couple of components to this path node. So we're going to add a mesh renderer and a mesh filter. This is just so we can sort of see it for debugging purposes, so we know whereabouts our nodes actually are. So I'm going to place these at each corner of the map. So first of all, I'm going to place the path in the middle, so the actual main node. Just bring it up to the ground level. So this first path node in the corner. Then duplicate out. Then this one is going to go to the upper corner. This one is going to go to another corner. And this final one should go to the far corner. Oops. Sorry, 4. Yeah, there you go. So then we've got these nodes. And then what I'm going to do is about here, I'm just going to create another sort of another subpath to sort of show off what this can do. This is for yep. In this case, then I'm going to duplicate that, drag it to there, name it back to path node, so it's resets the counter for us. Get rid of that. Right, so stick it out by 4, so let's get rid of that. Actually, no, sorry, the person wants to stay there. I duplicate, send that out by 4, then duplicate again, and bring it back. Okay, so the idea is I go from here to here, to here to here, come here, go up there, come down, then head back to the beginning and just sort of complete that loop. So that should be how our code is able to read the path and move our AI along it. So we've created our path generator script, so let's jump into that and start working on that. Right, so we've got our code open now, and for the code, what we're going to do is we're going to need we're essentially going to need a list of the nodes, of path nodes. So system collections generic gives access to a list of, and we're going to make a struct up here. This is pretty much going to be our node data, so I'm just going to call it path node. Oops. So this gets store data for sort of what each point on the path has, so you'll understand how doing this is good now. So public, we're going to want a transform, so this is in the unit you see in those sort of path nodes that we actually made that are transforms, this is what that's going to be. So call this transform, simple. The distance, this is going to be, this is going to be used for sort of from the last point to our current point, how far along the way. And then we're going to have a minimum distance and a maximum distance. So the idea is, what we're going to do is we're going to be able to essentially call a function that we're going to call place along path, and it's going to sort of use the min distance and max distance to quickly place them along path. So it's an optimization essentially for finding out to place them on paths. But yeah, again, as we go down, you'll see sort of why that comes into play and understand why we're doing it. So what I'm going to do is add a full for loop. So you place this path generator onto the path, sort of path object that we created the scene, and then if it's looped, it'll create this sort of path to be looped. So you understand it that way. Make a list of path nodes. Into our nodes, and new list of path node. Then a float for the total distance. And this becomes, why is this not working? That's this one. Yeah, this becomes important a bit later on. It's essentially going to hold how long the total path is, and it's going to let us access stuff faster. But yeah, again, you'll sort of find that later on. So well, we don't need this update function. We can get rid of that. What we do need is a function called find nodes. So find nodes, and we'll pass in a parent solving transform. So in the find nodes function, what we're going to do is going to go for each transform child in parent dot children. No, in parent. Sorry. Yeah, it's parent. Yeah. So essentially, what that does there is that sort of main path. So the thing that we've got called path in our unit scene, this will get the children of it. So this will now loop for all of its children. And what we're going to do if child dot count equals 0, so if it doesn't have any children, then we're going to do path node new node equals new path node. Just missed up brackets, swap sticks. Then new node dot transform equals child. Then underscore nodes dot add new node. So create a new node first of that child, and then sort of make this iterative, so it'll essentially go through each. So I'll go for the sub ones to create the small paths as well. Essentially called find nodes again. Find nodes child. So for any children, it'll pretty much try and find the nodes in its children. So yeah, that should pretty much generate that should collect all of our nodes from the object in the scene. So what we'll do is first we'll call find nodes, and the parent is going to be just transform. Because bear in mind this is going to be placed onto an object. So the transform will just be the object sort of transform. Okay, so what we should do next is, I think, probably we'll calculate the actual path next. So create something called calculate path. Now for this, what we're going to do is pretty much loop through all of the nodes that we just collected from the find nodes thing and generate distances for them and put them in sort of the path node stuff up here. Then we can use that for easily placing something along the sort of overall path that we've created. So what we want is a float, and we call it can't do that now. Total list. So sets to 0 to start with. Then for and 0, that's the okay, path node. So the current node that we're working with, so that'll be nodes and the next node, which we'll define a lot further down. Well, actually, yeah, define now. If loop and then 5 plus 1 is equal to n-1 nodes dot count. Then the next node will be called nodes 0. So what we're doing there is if it's looped and we're going to be hitting the final node, we essentially want the next node to be 0. So that way it'll make a continuous loop around the full circle. It's kind of well, yeah, again, it'll make more sense later. It's one of those things like sort of preemptively doing this. So else if I plus 1 doesn't equal underscore nodes, then we should be able to just go next node is I plus 1. So next node equals underscore nodes I plus 1. Else, so neither of those two are true. Then next node equals new. Okay. Yeah, essentially, the reason why we do this part of the bottom, sorry, I was just picking up. we have to do that because otherwise we'll get complained about by the compiler saying, oh, next node's never set to anything. Where really, this won't really happen. This is pretty much impossible to happen because these two will pretty much always definitely happen. So yeah, this will never really be an issue. So what we do is float this equals 0.0 and if next node transform. Yeah, so in case this does happen, so pretty much if this does happen, we just want to make sure that we're only sort of doing this if there's a transform. If there isn't a transform, then it'll end up crashing. So in the very rare case this does happen. Let's free the distance. Node transform position. Next node transform position. So getting the distance between both nodes. Then we can do current node dot dist equals dist. Current node dot min dist equals total dist. Then we'll do total dist plus equals dist. And current nodes max dist will now equal total dist as well. And then sort of set the data as node equals current node. Yeah, so we'll sort of flow through that bit there, but essentially what we're doing is get distance between the nodes. Then we're saying, okay, the current node's sort of total distance is that much. The minimum distance, so to get to this node from the beginning, is currently our total distance. Then we add on the distance between the two nodes to get sort of the end point of that, which we can just store as max distance. But as this goes through, obviously total distance will go up with everything, so yeah. And also total list equals total list. So let's store total list out there. Cool. Yeah, so that's our calculate path. So we'll want to call that straight after find nodes. So call it up here. Calculate path. Nice and easily. Now the next one we're going to write is going to be the get pointer path. So this is what all of this has been sort of working towards. So what this will do is what we're going to do with this is we're going to allow them to pass in a progress, which will be between 0 and 1. And we're also going to do a reference out of pos. So you'll be able to get the path node for sort of the progress in case you want to work with that for some reason. And you'll also be able to pass in a vector 3, call it whatever you want, and then it'll sort of return the value of the position for that amount of progress in the current path. So let's sort of get that sorted now. So if loop then progress equals progress minus math of floor progress. So pretty much because there's 0 to 1, if the whole path's loop, say we got the number 1.2 or something, then we're probably going to want 0.2 instead. So what mathf.floor does is first rounds a number down to the nearest whole number. So if it's 1.7, it'll round down to 1. If it's 2.2, it'll round down to 2, sort of thing. So then we can do the progress minus whatever sort of the lowest whole number is to get the decimal point of it. Then else if progress greater than 1.0. So just clamp it here. So just making sure if someone passes so that it's too high, then it just sort of gets set to the maximum that we're using for sort of our path stuff. So there's less than 0.0. There, progress equals 0.0. There we go. Yep, so that's pretty just clamping stuff down for the progress value. So what we're gonna do here is float current this equals I'm just going to tell this times by progress. So translating that sort of 0 to 1 progress thing to an actual distance. And then an int id. So because mathf.floor returns to float, we want to cast it down. And what we're doing at this point is essentially we're going to get the halfway point of the nodes list, and using the min distance and max distance we got earlier, we can find sort of the point on the path faster this way. So do m_score nodes.count divided by 2.0. So obviously, say count was 3 and we divide by 2.0, it's going to be 1.5. Just make sure it drops it down to 1. And the reason why we're going down and not up is essentially in case somewhere, if it's 1 and we do it, then 0 is obviously the one we want. We don't want 1 because if it's 1, then we're going for a wrong part of the array. Okay, so now we're going to do a while true loop, which is always lovely. So while true, if m_nodes id dot min_dist is greater than the current dist, then id minus else if m_nodes id dot max dist, that's the current dist. Yep. Sorry. id plus. Right, so with that, pretty much what we're doing is moving the sort of index up or down, try and get to the right node that we need. So based on our distance stuff that we had before. So nothing too complex there. And else if the m_nodes id dot min_dist is less than or equal to current dist, and then m_nodes id dot max dist is greater than or equal to current dist. So just sort of safety check there. It should definitely be that, but just, yeah, again, just for safety purposes. So float look. So this is getting the progression between the two nodes based on sort of like the current dist we pass in and all that. So this is a bit mathy and uses ternary operator things. So we'll go on, bear with me on this part. id dot dist is equals it's yep. There we go. Yeah, so that's nice. This opens up. Things open. It's probably just very minus m_nodes id min_dist divided by m_nodes id dot dist. Okay, so essentially what this does is if distance is equal to 0, then we just give it a 0. There's no point doing the math. This avoids that avoids what we call divided by 0. Yeah, that's don't know why I thought it was called to it. Yeah. So what we do is take the current dist, take away the minimum dist to sort of get the difference in distance at that point. Difference in the distance at that point. So the current distance along between the current nodes, and then we divide it by the total distance of the nodes. So if you imagine, say our current dist was 15, our minimum dist is 10, and the total distance between sort of the total distance of this node is 10. So it'd be 15 minus 10 is 5, then 5 divided by 10, so we're halfway along, so it's 0.5. So that's pretty much what that worked out. Right, so now the pos that we passed in up here, we're now going to do vector 3.alert. So we do alert progress, m_nodes id transform position, and m_nodes id plus 1. I don't know if this is the best place to put this, but it just makes it easier for sort of keeping this smaller than it needs to be. M_nodes count position 0 provides id. So pretty much if the ID goes over the node count, then just give us either 0 or just give us the actual thing if it doesn't. Going to transform the position, then Yeah, again, you can break this all up into like sort of if statements if you really want to, but this just seems sort of quicker for keeping it in that small space. Then what we'll do here is return into nodes. Yeah. So essentially, if it enters here, it's definitely going to give you back sort of what you want. Now, what we're going to also do, final part of this, is going to add a public float called get total distance. Okay. And then we'll turn total distance. Right. So that's everything for the path generator stuff. What we're going to do now is write a couple of scripts just for sort of using the path generator to move the enemy along our path. So let's jump to that now. Right, so back in the editor, what we're going to do is right click, create C# script, and I'm going to call this progress along path time. Really catchy name, some greatness. And create C# script, progress along path speed. Now you're better to right click and do create C# script. Oh, you can't see on the screen, that's annoying. Yeah, but you're better to do the right click create C# script stuff. So otherwise you'll end up with weird issues with Uni. It's not a fan of things being copy pasted around sometimes. So it's much easier to do that way. Also it sort of pre-writes them in here for you. It pre-writes them in the code window for you. So let's jump back to code and quickly write these two scripts and then get this guy moving along the paths. The code part of this is going to be nice and simple and pretty short, so let's quickly jump into this. So what we're first going to do is write public path generator path equals null, and then public float speed equals. I'm going to put a default value of 5, but actually no, sorry, 5 is super fast. I remember it. I'm going for 2. Yeah, I'm going for 2. We don't need the start function in this case. What we do need is a float progress step. Install progress. I'm going to decide to nothing. Now what I'm going to do here is I'm going to stop progress plus equals bracket 1.0 divided by the path. We get total distance. So that's using why we added that function. Times by speed times time. That's 10. Essentially, because we know a path is 0 to 1 in terms of progress, we can do 1 divided by the distance to figure out how much one distance is, and then times that by speed, so you go along at that speed, and obviously delta time to make it frame independent. So that's the reason why we're sort of doing that. Okay, so now that we've worked out the progress value, what we need is vector3 pause equals new vector3. So just put it to initialize at that point, and then path, they get point on path, passing on progress, and pause. Then do transform dot position equals pause. There we go, nice and easy. So now that just passes our progress into I get point on path stuff in wherever it's gone, like path generator. Yeah. So I'll go through this, pop out our position stuff, do the reference stuff, yeah, same stuff like that, and then set the object's position. So with that done, so we should now be able to progress along the path at the beginning speed, and because this is so similar, I'm going to copy that, paste it in here, and then what I will do is, instead of this, what we want to do is actually a lot easier. It's just time delta time divided by, and I'm going to change this to the time. The default says 10 instead this time. Time, no, okay. Time, yeah, not the time. Yeah, that should work as well. So super easy for sort of swinging between speed and time stuff. And now we should be able to go to the editor, and it should, fingers crossed, all work. So let's do that. Right, so going into the editor, we've got an issue. Some invalid things. So let's jump over to that and see what's going on. Right, so it's complaining about pause. And I missed. I have to put ref before that. So you go like this, both places. Yep. So yeah, let's put ref before the position. It just Spirit says we're passing this by reference to the function. And passing by reference just means we're allowing us to change values of that thing. So yeah. Now let's go back to the editor and that should work. Yeah, there we go. That all works. So first thing I do is select our path, grab the path generator, throw it on there, and I grab it looped. So that's all we need to do for the path generator stuff. Nice and simple. Then if you click on the enemy, what you're going to do is, I don't know what's going on. Yeah, take this one, throw it on it. So put some path time, and grab the speed one, throw that on. Now I'm going to tick this box, turn speed off for now. So it'll be going by time. And then we'll drag this and drop it onto both of these. So there you go, it's now linked our path generator to that path. I'll make it a little longer, so watch it go around. So now I should click play and it should follow the path around. So, yep, as you can see, it's moving along. About turret attempting to fire at it. Yeah, so it's moving nice along. It's right now, as you can see, it's not actually facing the right way as it moves. So we're going to quickly fix that up. That shouldn't take us too long to do. Yes, yes, that's meaning. Yeah, perfect. So actually it loops round. I'll fix that in a minute. Yeah, so it just loops round and does that. Cool. Sorry, this was just me playing around before this, so it's got a wrong script, so ignore that. With that error, let's look at CV. Right, so we know our time one works. And I expect the speed on to work, but let's just check just to make sure. So that, play, and go. Yeah, so as you can see, it's off, moves around, it's getting all the stuff properly. It's very slow, so I'm going to speed it up. It's probably going to be very fast now. Yeah, it's not too bad. Yep, so point, and then loop. Sweet. And now for us to turn the loop part off, and we'll speed up again, and play. There you go. So because that was the final node, it's gone back there. If you want it to head back there without being loops, just kind of create another node there. So in here, after sort of this one, you'd have 0.5, that would be the first node. Yeah, again. Or you could rewrite code a little to include it if you want. That's up to you. That's up to your choice. Right, so as you can see, it's sort of an issue with rotation to thing. Well, it's an issue. Right now it doesn't rotate at all. So what we're going to do is I'm going to add a 3D object, a cube. You're going to scale it down just slightly, so 0.5. Yep, so 0.5, 0.5, then 0.5, and I'm going to bring it out forward. Right, so there you go, so we've got a little face on the cube. So now we know which way it's sort of facing forwards. Okay? And we're going to we're going to create a script and go call it rotate to movement. And this is going to handle sort of make sure we're facing the correct direction. So let's quickly jump in and get on sorted. If you really want to, you can actually put this into sort of the path generator stuff to get a rotation as well, sort of based on it. But I'm going to sort of do this in a more lazy way. But yeah, it's more lazy way. Okay, so public float turn speed, off, and then that's free and install last block. So last location we saw it and sort of turn speed of the object. So to begin with, we're going to set last lock to transform position. That's easy. Then in the update, what we're going to do is if n underscore last lock doesn't equal transform, position. So when we're moving, rotate essentially. Then vector 3 equals transform position minus. So which way to sort of rotate towards? Normalize that. Normalize that. There we go. So once we've written the normalized bit, it's going to be quaternion look rot equals quaternion dot look rotation. It's passing the sort of direction that we've got. And then just do transform rotation equals quaternion dot rotate towards passing our rotation, passing the look rot, then do turn speed times time, time. Yeah, again, making it frame independent. Then at the bottom, M1 is the last one, equals transform dot position. Yeah, okay, so that way we're just updating that last location. So now that when placed onto the enemy should make it look towards the path the way it's going. So let's jump into the engine and see how that works. Okay, so in the engine, just select the enemy, then find wherever it rotates movement is, there is. Scroll, and then put it on. There we go. So rotating movement, I've got turn speed is 3. I don't know what we're going to set it to, let's see. So I can apply and see how it turns. Very slowly. Or not at all, I can't fully tell. Let's go for 90. Jump it over and wind it. There we go. So yeah, it's rotating towards it. But yeah, it's increase that rotation even more. I'm going to increase it even more. Just play around with this value, obviously, to sort of get a good thing. But yeah, that seems a bit preferable. Right, so now as it moves between them, it sort of rotates, and yeah, perfect. So now that'll rotate as we move along. Throw it into loop mode. Make it go super fast. Obviously, because of the speed that the enemy is moving at, the rotation stuff looks a bit odd. But if we slow down with this timeline, then when it gets to this node, it should look a little more. Yeah, there we go. So it looks a lot less sort of like, oh my god, you span while moving something. But yeah, there we go. So that's sort of doing the enemy's movement. In the next video, I will be doing smart turret tracking, so aiming where the enemy is going to be moving to. So that was the reason why we wanted this. So when the enemy's sort of moving along here, we'll be aiming ahead of where it is to make sure that the bullets hit. Because right now, as you can see, most of the bullets are sort of going behind. So we'll be aiming ahead to make sure to hit the target. So, look forward to the next video. Thanks for watching. Bye.